Today's presentation is quite a lot of new stuff that I've been investigating recently. So it's really exciting to come and share these findings today with you. And the topic is the benefits of Kubernetes and cloud native patterns. And this all will be in this kind of, the first thing, it won't be a sales pitch for you to adopt anything in particular. It will be offering, hopefully, a kind of a new mindset, a new way to think about things in this context, and offer some lessons learned from those who have been doing this for quite a long time, that also have shared their experience in these kind of industry conferences or in research papers. So I'm using content from them, and also it's kind of nice to see that with this open source, everything that I'm going to talk about today is open source. And it's been interesting to see the latest years when people in open source, large end user companies and large solution providers like Microsoft and Amazon and these Google and so forth, Twitter, come together and focus on, okay, what can we do together? Because we are all facing these really hard problems. How much can we share? Can we push this state of the art even further? And by doing that collaboratively, we don't need to have each and every company much capacity on their own to still deliver world-class solutions. So it will be more about that, the kind of open source mindset, but it won't be about how to use Kubernetes. If you're interested in that, maybe we can have another session later, even on kind of more practical, more hands-on. But that's not the topic of today. And also, I can link later to this kind of workshop, hands-on workshop that I did in Tampere 2 years ago. I think, yeah, exactly 2 years ago. And that was like 3-4 hours where people we gathered in an office in Tampere, and then actually a hands-on hacked on things such that you would get a Kubernetes cluster up and running and have a web service and upgrade it and see the traffic flow from the internet and all of that. So, but that's not the topic of today. Today is more about like the underlying concept, the way of thinking, and what you can bear in mind when you're designing your own data center systems. So shortly about myself, I'm Lucas. I'm from Jakobstad, speak Swedish. I'm from a third-year student now at Aalto University. I'm 6 years-ish ago, I discovered this Kubernetes thing, thought it was kind of cool, and essentially just went to GitHub and said, hi, I want to contribute. Where do I start? And how can I help? And that was my hobby for a couple of years, or 1.5 years to be more exact. And then I started getting these job offers on how to do that also professionally. So I've been maintaining Kubernetes, being one of the Kubernetes maintainers for some time professionally, and been doing all kind of ambassadorship programs and special interest group leadership and these kinds of things, and also speaking at these KubeCon conferences that happen 2-3 times a year. So that's been all really exciting, really cool. Been building different kinds of tools in upstream Kubernetes that now is in production in data centers all around the globe. And the company that I've been working with mostly is Weaveworks, one of the cloud native startups that has, now is a global startup with employees from all around the world because of remote working. And I've been contracting with them for the latest five years. And since 4 years back, I'm also doing meetups in Kubernetes, meetups in Helsinki, Tampere, and Turku. But sadly, that's not been possible to do it the latest 2 years, but hoping to get back to that in a bit. So what are we going to talk about today? We're going to talk about the cloud native history, definition, projects, and benefits. So what is this, like background context, what is this all about? Then we're going to talk about the dynamics of server systems. Dynamics is actually happening at kind of larger scales, and when you're going into production, I hope and think you will relate to these kind of stories quite a lot, and then offer some solution how we can deal with these challenges in a chaotic world, and that's through then declarative APIs and platform abstractions. And don't worry about these names; these are all very fancy words that mean specific things. We'll go into all of this, and then going a step further. Once we have that, how can we kind of take knowledge that humans have on how to operate different kinds of systems and encode that in or codify that such that we can sleep well at night and the web servers are still running well and responding to user load, although the Chinese wake up and start using our website. Then some examples of this, for example, how to manage like MySQL clusters that have like millions of requests per second, and how do you kind of build a team workflow around these Kubernetes things with GitOps, and then a little bit about Kubernetes in the end. So software is eating the world is one of the famous quotes from Mark Andreessen that wrote an essay about this in 2011. And essentially, it's an observation that every industry, regardless of what it's doing, will need to face digitalization in one way or another through automation in software and streamlining of processes through different kinds of automated systems talking to each other. So like Internet of Things and robotics and these things that this project is all about, right? But so that was an early observation, and first this kind of started slowly and got into motion, especially the recent years when we have these large scale users like Google and Twitter and Amazon that have built super large clusters, super large data centers, and then also run into problem after problem after problem, and they have needed to find a way to fix those problems, to work around them, and to solve them. And what's happened in the recent 5 years with Cloud Native is that they have actually opened up and shared their knowledge, shared their experience, and so on and so forth in research articles and in open source. So for example, Kubernetes, which is now the world's second largest open source project after the Linux kernel, which is kind of funny when the Finn Linus Torvalds created that. So it's the second largest project now, and it was kind of started as a thought experiment inside of Google, where they were thinking, okay, we have 2 existing systems that are running everything from YouTube to Gmail to search, to Google search, and every other Google Docs service and similar things that Google have. Those systems are called Borg and Omega. So they published 2 research papers in 2013 and 15, I think. And there they described how they're dealing with these challenges and what they've learned. And then when they got further on what have they learned, they were thinking, okay, if we redo this system and make it better and apply the lessons learned, what do we get then? And from there, Kubernetes was born. And then after it was published as open source, after that is kind of this crossbreed between every large and small company's ideas about how to best manage server infrastructure. So that's kind of an interesting way of it's coming from some large place, and sometimes it comes from an end user as well, not like these tech companies, and then they get out in open source and become kind of massively used. So when Kubernetes was starting to gain traction, there was a clear need to find some organization that would actually host the immaterial property of Kubernetes. and kind of, so it's not Google's property. It's not a single company that's owning it. It's shared and for the greater common good of the world. And that's why Cloud Native Computing Foundation was established, to have this kind of umbrella that every company can contribute to and not be afraid that someone is stealing anything. So it gives kind of this trust and neutral ground for people to collaborate. So drive adoption of this technology. Internet scale things. So like you can go essentially global with your things immediately. And I think in the really early days, like 2015, I think, when Pokemon Go was a thing, they used Kubernetes as they built directly on top of Kubernetes, and the first day it was like billions of users. So of course they had some problems, but it wouldn't have been possible before. And Cncf wants then, through this cloud native technologies, to improve the developer experience such that you get faster code reuse in the open, and you can build on top of the shoulders of giants, which is this kind of good phrasing. Then improved machine efficiency. A lot of these projects, they tend towards figuring out how to most effectively use the resources available. And this is quite important because it's been found in some studies that approximately 2% of the world's CO2 emissions or carbon dioxide emissions are coming from data centers. And that's quite kind of a lot. It's on the same level, in the same magnitude at least, as the airplane industry, but it's much less well known about this. So it's not free. These data centers are not just a thing that is infinite resource we can just use without impacting anything else. We need to think about machine efficiency and using our resources well, and that's what this is all about. Then if you had 100 servers before, and now you only need 50 because of this increased machine efficiency, which is quite common with Kubernetes, then of course you reduce costs, both in terms of energy and space and all these kinds of things. And then you get faster velocity as well. You can develop faster. You can keep your things maintainable in a kind of novel way that had not been possible really before this mindset. And Cncf started out with these companies, the logos now. It's kind of too much to put in a slide, 738 members. And just kind of funny to, just insane to see the market cap and funding of 23 and 24 trillion and billions respectively. It's, yeah, just, I don't know, incomprehensible. And so why does Cncf exist? They had this kind of landscape started as a thing where anybody that had something that they thought was like cloud native-ish, and we'll get to the definition in a bit, could send a pull request on GitHub and say that, you know, here is my project, we're doing this. And well, it started small, you know, like a couple of tens of projects or something. Now it's referred mostly as the cloud native hellscape, because it's so many options. It's so hard to navigate. How do I know what to pick? And that's one of the places where Cncf plays a role, because they have this kind of technical oversight committee, which chooses some of the most high value and technical merit projects that are of good stability and so on and so forth, such that a user looking at this map can see that, okay, Kubernetes is a Cncf graduated project. I can trust that. There's a lot of production users. There's a lot of maintainers, good quality of code, etc., etc. It's past all the kind of benchmarks to get to that position. So you can have kind of trust in the Cncf projects, which are then graduated. And that follows this kind of model of the bell curve, famous bell curve, where the crossing the chasm book essentially identify different kind of user personas in terms of adoption rate. So like there's innovators and early adopters, and then there's this kind of large chasm. And then when it's crossed the chasm, then this kind of gets really a lot of adoption at once. And Kubernetes is definitely, it's crossed the chasm, and that's the kind of difference between the incubating and graduated stage. And now it's in use in thousands of places. And there's quite a lot of CNCF projects now that are graduated. So I can't count them all here, but more than 10, I think, at least. And then there's quite a lot of these incubating projects as well. And even more on the sandbox level, the kind of most early stage, try this out thing. But if this still feels overwhelming, then the CNCF has also made this kind of trail map such that you can see that, okay, containerization is probably the first thing I want to be looking at if I'm actually going to use this, and then maybe set up some continuous delivery pipeline so that when I push to Git my source code, then it actually gets delivered somewhere so I can look at the results automatically. I don't have to run the test myself, etc. And then first we get to Kubernetes. Maybe now I want to look at Kubernetes and application delivery in that sense. When I have it running Kubernetes, maybe I want to take a look at how it's doing. How is the application doing actually inside of there? Is it kind of too much resources allocated, too little resources allocated, or are there other problems related to it? And then it continues like that. So let's look at the cloud native definition. What is it even? Well, this is still on a very abstract level, but we'll get to some examples in a bit. So scalability is one of the first things. Cloud native technologies empower organizations like you to build and run scalable applications, okay, in modern dynamic environments, such as public, private, and hybrid clouds. And this is a source of confusion sometimes. So public cloud refers to some of the kind of a company that is dedicated to host data centers. So it's a data center provider. So like that's Amazon, Microsoft Azure, Google Cloud. There's Finnish versions of it as well. UpCloud. There's Herzner in Germany, and then like DigitalOcean, etc., etc., etc. There's a lot of these, and you can use a public cloud. That's completely fine. You can host your own data center, also sometimes referred to as a private cloud. And you can use a mixture of these as well. That is all fine. Or you can use multiple of these clouds at once. Kubernetes allows you to do that, and so on and so forth. Then there's some examples of what is cloud native, and here they have containers, service meshes, microservices, and they kind of exemplify this approach. And containers is maybe the key thing we'll take a little bit a deeper look at today. The service meshes and microservices are for another presentation. And if you do that, what does it give you? It gives you a resilient, manageable, and observable server stack. So resilient means essentially the ability to self-heal, so that although something goes wrong, and it will, you can recover from that situation in some way or another and get to the known state that you want to be in. Then if you have that procedure, then you can also call it kind of manageable. And then observable is quite important as well, to see how the applications are doing. And now that you have those things, you can kind of move pretty fast with your application code. You can make high impact changes quite often, and still have a sense of predictability and punctuality when things are going to be deployed, how they are going to be deployed, and so forth. So for example, certificate rotation is one of the things that is quite daunting to do by hand. You need to do it every year, or with Let's Encrypt every 3 months. If you do that by hand, it's kind of a lot of toil. It's kind of a lot of changes you need to coordinate at once. But if you rotate your certificates every week and have automation for that, then it's not as much toil, because you're doing it always, and it doesn't add extra burden. So all in all, it requires a new mindset. It's a server management paradigm. And paradigm, I just checked the definition here, is a theory or group of ideas about how something should be done, made, or thought about. So that kind of summarizes it. And this paradigm comes then from the large scale users and as a kind of crossbreed of a lot of these. Well, these 738 companies in Cncf, for example. But I want to point out two misconceptions early on, so that's kind of cleared out. Cloud native is not the same, or doesn't mean necessarily that you must use containers, and it doesn't require it. So it's not the same thing. Containers are one of the most common deployment forms, but you can still be fully cloud native and run things on your host or in VMs or in whatever other way. That's completely fine. Containers are a specific packaging mechanism such that you can put your application, you package your application inside of that, and then you can move it anywhere. So like, well, the analogy comes from real containers. So like regardless of what you put in a container, do you put an elephant or a goldfish or I don't know, bananas, then like it looks the same to the outside. So there doesn't need to be in the harbor, there doesn't need to be one specific goldfish like transporter and one specific elephant transporter. You can transport all of them using the same format, and that's a container, and then put them on trucks and whatever. So that's the kind of analogy that we want to use, so that once you put your application in this format, in the container format, then you can move it anywhere. And the focus is like on applications. And Docker kind of found the sweet spot in 2013, or from 2013 on, with the format, with the distribution, with all of these things. And kind of we're able to minimize or go from minutes to milliseconds in terms of deployment time compared to VMs. And they went from gigabytes to megabytes or even kilobytes in terms of image size. So now it was a whole other story to kind of redistribute this and to run it in different kinds of places. But yes, VMs also have their place. They're not going away. It's not a dramatic battle of any sort. They have their niche use cases. And other technologies also, other isolation technologies also have their own use cases. And kind of to see how we ended up with cloud native and containers, we started with non-virtualized hardware, so like dedicated machines for different use cases. And then we found out that, okay, we can actually put multiple applications, multiple machines inside of one machine using virtualization. And that happened in 2001-ish. And then once that was, then some business and technology persons figured out that we can actually sell this if we make this data center, put it open to the internet, and then just sell it as a service. Then we have infrastructure as a service. Then Heroku was like, okay, infrastructure as a service is great. Well, you get a virtual machine if you like, if you click some buttons in Amazon UI, but that's not what I want. I want the website to be running. I want a website. I don't want a virtual machine. So I want this kind of higher level tool to use. And I just want to do git push. I want to have my application written in Java or Python or whatever. I want to do git push, and then boom, it's online. That's what I want. And that was then the beginning of platform as a service. And then this all repeated with open source tools. Then Docker came along and with containers that streamlined this application delivery mechanism further. And then these kind of hyperscalers and companies started thinking together that what are the best practices for server management? And then we had cloud native. And cloud native also isn't cloud. This was the slide I showed a bit earlier. You can be cloud native and run your applications on a Raspberry Pi. So one of the first things I did with Kubernetes was to port this large kind of Google-made initially system to Raspberry Pis that cost $35 each, and run on a just ARM processor that essentially equivalent to what you have in your phones. And Kubernetes runs on that. Kubernetes runs fine on that. You can run containers. You can run all kinds of applications on top of Kubernetes, web servers, and I think there was one person that tried running 2,000 Nginx web servers on one Raspberry Pi already like 8 years ago or something. So it's quite powerful, and you can put it there, and you can use a lot of cloud native patterns there, no problem. You don't have to go to Amazon. You don't have to buy a huge data center from someone. You can apply these practices still without going into public cloud. That's not the same thing. So then, why adopt cloud native? Higher resource efficiency. I was talking about that. This is quite important as well for not just for the bottom line, but for the industry and world as a whole. This is a picture from Google's data center in Hamina, where it's an old paper mill, I think, that they are using all of the existing infrastructure in terms of water delivery. So the water from the lake actually cools the servers, which is quite cool, literally. And then combined with Borg and Omega that they're already running internally, they have hugely efficient efficient resource usage. Then resiliency. We'll talk more about how this is resilient later, but with resiliency, you can go faster, and you can go you don't have to wake up 2 a.m. at night because someone at the other side of the globe started using your website. That's kind of annoying, just to scale up. And then portability and uniformity. Portability, for example, achieved through containers, but also through defining abstraction layers and building these kind of reusable tools or Lego bricks that you can use inside of your to connect different projects together, and uniformity comes kind of with that as well. So it doesn't matter if you have your application in Google Cloud or in Amazon or in Azure, it still looks the same to your application. It doesn't even know. And with the reliability, with the uniformity, we get also a higher development velocity. So we can go from development to production in minutes, not weeks or years or that kind of time frame. You can run all of the tests. You can have this kind of pipeline and automatically make sure that everything works when rolling it out and testing it in user traffic, automatic monitoring, everything can be automated in that regard, and then you can get really quickly your new features to your customers, which is what the business at the end of the day is all about. You want to deliver value, and Cloud Native lets you do that. But now the question, there's been so far it's been quite a lot of buzzwords and all of this, this works. But now the key question is why and how and why wasn't this available before? What is actually different from the ways we have been doing this pre-Cloud Native? So the kind of one of the key I'll stop just quickly and check the chat if there's any questions, or if you have any questions, then let me know. I'll make sure I pause for some seconds. Okay, then I'll continue if there's no questions at this point. So one of the observations in actually what you learn in high school, in that or even in elementary school, is that the entropy, the unorderedness, the chaosness of the universe is actually expanding all the time. It's increasing, and the chaos inevitable in physics, and that also applies to server systems. It applies to information theory. It's been kind of found that these two are proved that these two actually align. So given that chaos is inevitable, how can we deal with it? Like, the first thing is, like, we need to realize that it is inevitable and we need to do something about it. We can try to reverse the chaos. So for example, before you eat dinner or before you make dinner, everything is maybe order, all the plate and everything in your shelf is ordered, everything's good, but then you make dinner, you eat dinner, and then you have a lot of dishes to do. Now it's more chaotic than before. So what do you need to do? Well, you need to do your dishes and or use the dishwasher to reverse this entropy increase. So that's what we want to do. But how do we decrease the entropy? And well, this is one of the I have a practical example of the entropy increase here that hopefully you can relate to, and this is kind of a tale of just how it is, how this job is as a system administrator. So you get 3 new servers. They are perfectly in order, perfectly consistent, same operating system, same configuration. They are all powered on. You need them, you use them. That's great. Your users are using them. And then after some time, a critical operating system upgrade comes along, and it's about security, so you need to upgrade quickly. Okay, you upgrade 2 of the servers, but the third one you're afraid to touch because it's really, you know, critical. It has some critical things on there, and that can't be disturbed at the time. So it's like, okay, I'll wait for, I'll do that next week. Okay, but now realize that, or like notice that in these histograms that I have on the side that kind of measures the orderedness of the system has now it's become a bit more unordered already, because now there's 2 servers on V2 and there's 1 server on V1 still. Okay, but it's not that bad. But then server 1 starts complaining about something, slow disk access time or some configuration issue of some sort, and then sysadmin A goes in, fixes it, imperatively clicks web UI or edits configuration files or something like that, fixes the issue, the server 1 stops complaining about the issue, and now it's all fine. Then sysadmin A goes and does something else. But notably, the 2 other servers are not fixed, they're not patched, they're not consistent now anymore. Then due to a seasonal trend, one of the servers is shut down to save energy and cost because it's not used at the moment. Because, for example, if you're selling summer products, then in the winter maybe you don't need as much, you don't have as many customers. Okay, turn off that. Then sysadmin A goes on vacation, and now the third server starts complaining about the same issue, and unfortunately sysadmin A didn't document what they did, and isn't reachable. So sysadmin B goes in and solves it in their own way, that is different from how server 1 was configured. So now we have configuration C, and now notice that all of the servers are suddenly in different states. They have different configurations, and then there comes along a new version 3 upgrade to the operating system, and it contains some good feature, some wanted feature, but it also, upgrading always comes with a risk. So they use this kind of canary mindset, that you upgrade only 1 and see how it goes, and then you can roll back if not. So they upgrade 1 server to operating system version 3, try it out, and this is a so-called desired state change. So we want to change the state. And we do so. But now also notice that the operating systems, all of them are different now, actually. And then a thunderstorm comes in over the city where the servers are, and boom, lightning strikes, and one of the servers is out. The power supply is out. This is something random. This is something that's emergent that we maybe didn't, that just happened. We can't do anything about it directly, and we need to respond in some way, but we can't prevent it completely. Well, maybe no. Well, maybe in this case we could have prevented it with some over voltage protection, but I hope you get the meaning. So we started in the beginning with something that was completely ordered. Everything was the same configuration, and at the end of the day, everything is now different. Everything is kind of much more chaotic, and thus the entropy has increased. So what are the key takeaways of this kind of analogy is that the systems are inevitably becoming less ordered, and it's not our fault. It's just the way universe is. But what we can do about it is to have some periodic corrective action to make sure that we steer the course of the system towards some desired state that we want. So we need to define somehow, where do we want our systems to be? What should they look like? How should they be configured? And then we want some process to actually get there. And an analogy to this is that when Alice in Wonderland comes to Wonderland, she asks the cat that where should I go, or what road should I take? The cat counters with, well, where do you want to go? She says, I don't know. And then the cat says this famous thing, or quote, that if you don't know where you're going, any road will take you there. So if you don't declare any desired state of your, like where exactly in what state should the systems be, then anything you do will be right. Any road, any state will be okay if you don't have one that you have defined that this exact state is okay, and none of the others. And then I want to highlight this great book about randomness. It's written by Nassim Nicholas Taleb, and this talks about these kind of unpredictable events that are quite unlikely, we think, until they happen. And then when they have happened, we say that, oh, they were super predictable because of, I could see it coming, like, although you couldn't if you would have been asked the day before. And if the unlikely event also carries an extreme impact, it's called a black swan. With the analogy that before people discovered in Australia that there are black swans existing, then just from empirical observation, we had assumed that all swans are white. And well, that wasn't that kind of, it didn't have a great impact, but what did have a great impact was the COVID crisis. Well, for example, all of the financial crises that have appeared, the penicillin discovery, and so forth. It doesn't have to be a bad thing. It's the penicillin, for example, was an accident, or like just some mold that had been left at the lab, and then when the inventor came back, then he saw, oh, well, this actually kills bacteria. Quite cool. Maybe we could use that. And because of this randomness that applies, and because of this entropy, in large-scale systems, at some point, failure is the norm. So everything will fail at some point, and that's the only thing you know, and you need to deal with it somehow. So Google, for example, in their Borg paper, where they describe how they're running their systems, deliberately leave significant headroom for workload growth. These kind of black swan events, like there's some trendy thing that pops up, and then YouTube needs to scale rapidly for that video or something like that. Load spikes, machine failures, power outages, hardware upgrades. All of these things are emergent. They happen. We can maybe enumerate them. We can maybe say that they will happen at some point, but we can't say when they're going to happen. So that's quite interesting. And another thing they observe is that a really small percentage of instances of something like machines will actually represent a really huge burden on the administrators, and thus have this kind of large impact from some small percentage. It's kind of similar to how it's in marketing said that half of your marketing budget is always wasted, but the problem is you don't know which one. Yes, well, actually I'll one sec, I'll need to fix one. Classic that I forgot to put in the power cord. Any questions at this point? Also, good time to take a break and see. And remember that you feel free to ask in Swedish, Finnish, or English. It doesn't. All is fine. And you can post in the chat as well. So if you and you can also post privately to me if you want to give direct feedback. Cool. But if there's no question at this point about this randomness, then I'll continue as well. So this means that if you have 10 servers and the probability of some server failing is 1%, then it will take you quite a long time to see that the server will be failing, and then you will think that it was your fault and you could have avoided it because of you could have done something X to avoid it, buy new server RAM or something like that, or buy this over voltage protection. But once you get up to the scale of hundred thousands of servers or tens of thousands of servers, then you will realize that no matter what you do, you will always have systems will always be failing. They will always be erroring. They will always have some variable latency added to them, regardless of what you do, and you need to deal with it somehow. So for example, if you want 100,000 web servers to be running, like applications on your servers, say you can have 1,000 servers, like machines, 1,000 machines, and then on each of those you want to run 100. Then even though you have something that automatically applies that state and tries to always run 100,000, then machines will probably start failing in the rate that you will never get to the desired state, no matter how you try. So instead, what you need to do is to adjust the desired state so it gets up a bit, so 5,000 more, for example, and then you will hover around the state you actually want to be in. And there's an analogy to that, and the kind of, ancient knowledge actually, that when you're navigating with compass, you do this by default. If you, assuming that the person using the compass knows that the geographic and magnetic north poles are not in the same place, they will actually look at the compass, see that, okay, magnetic north pole is that way, then the geographic north pole is this way. So they will offset the error of the compass automatically. And that's the kind of same thing for you need to offset the error rate that is happening in the system like that. And that means also that the rate of errors is the important thing, not the amount of errors. So like, if it hovers around some stable value where you still have control, then it's okay. You will maybe never get to zero. You will never get to zero, and maybe you will never get less than that even. But if they start increasing quickly, then you might actually need, then there's some problem. But that needs the kind of derivative might be more important of the errors than the actual amount of them. So this is kind of similar to constant velocity. So if you have this kind of system that is always in movement, always there's machines going down, there's machines coming up, there's applications starting to run, there's applications failing, that is kind of like you would be always in motion. But because you have this kind of system that fixes itself up over time as it sees these emergent changes, it's like you're always in motion and you don't feel necessarily when you are in motion but not accelerating, you don't feel anything. You don't feel any acceleration anywhere. But if you're standing still and then need to move somewhere, then you need to accelerate first and feel the kind of it takes energy to do that in a completely other way than if you're already in motion. The same example goes here for the certificate rotation. If you do that by hand once a year, then it takes some effort. Every time once a year that you need to upgrade the certificates, you will go and do it manually, and it will be kind of an energy-intensive process with a lot of toil. But if you rotate your certificates every week, then it's all fine. So you don't kind of feel the same impact of it. So yeah, then we get to the concept of declarative versus imperative. And declarative means making a declaration. Declare means to make known as a determination. So like give an end state. And what is an example of giving an end state in a language? It's the door is shut. That is some end state, specifically saying how something is. But imperative is the opposite, and that's an action. It's some movement in some way. And with declarative, you focus much more on the what, not the how as much. But whereas if you're imperative, then you focus a lot on the exact steps on how to get there, but not actually as much on what is it actually I'm doing. So for example, you can think of a high-level programming language like JavaScript. Then it's a lot about the what. I want to have this variable, I want to increase it, I want to do a for loop, etc. But well, in the processor, it's just zeros and ones, and then just how. It's just doing all of the how, but it doesn't necessarily know anything about what it's actually doing. So, but due to our world being quite imperative, we need some kind of actuator still. We need something that actually operates imperatively on the claim that we're presenting. So we present a declarative claim, then we have something that fulfills the claim, an actuator, and by the actuator fulfilling the claim, we will get some result. So for example, you want to draw a logo on the screen. You could hard code the pixels on the screen, like a PNG or JPEG file. You could say exactly this pixel is this color, this pixel is this color, and so on and so forth, and then you have a fixed image size. But if you want to do it in another way, is that you say, using SVG, scalable vector graphics format, you say that, okay, I have a circle here with this radius compared to this view box. And then I have a rectangle here, and I have a line here from this point to that point. And that's declarative. That's defining relations between different entities. So once you display it in a browser, you will actually, there will be different pixels on the screen depending on your screen size. And that's actually quite good, right? Because if you have this super large 4K or 8K screen, it will still look amazing, because if you have a circle, then the browser will have calculated pi with better granularity than on a small phone screen. And so that's a claim. You have some actuator that imperatively fixes it, like calculates it, and then displays the result. then an SQL query is also declarative. SQL says just what do you want to get back from the database. It doesn't say in what order to do like different queries. It doesn't say, okay, in this file you will find the users table, and in this file you will find the amount of purchases and that kind of stuff. It doesn't say go into that granularity. It just focuses on the kind of application level logic, the kind of the correlation between different entities in the system. And the database then fulfills these. It figures out a way to based on the different database files and indexes and everything, figure out what to show to you and what result to give you. Same things for contents. You want to read contents of a file. The operating system figures out, is this from the internet? Is it from a floppy drive? Is it from a hard disk? Is it from your phone? Where is it? And then figures out, gives you back the file content. If you have a list of numbers and you want to get the average of them, then you could or the sum of them or something. You could of course do the kind of dummy thing of like, okay, you make a variable with the sum, and then you loop through all of the integers or numbers in the list, and then you add them one by one, and then that's it. And then you maybe divide in the end. But that is not parallelizable. It doesn't use advanced hardware features. It's necessarily not as fast. So if you have this kind of declarative claim, so you can do it imperatively yourself. But if you want to do it declaratively, then you just present the list of integers, the list of numbers, and you say, I want to execute this sum or average function. And then depending on what hardware it's running on, depending on what processor and what is fulfilling that claim, it will calculate it will get you the result in different ways. So if you have 4 CPUs, then it will maybe use all of the 4 CPUs. And then, of course, I need to have to relate this to these examples to something concrete in this talk. Kubernetes functions in the same way. Kubernetes says that you say to Kubernetes, I want 100 containers running. That's an end state. And Kubernetes is the actuator that actually makes that happen. It starts all of those containers. If they fail, it will replace them somewhere else. So like this. The user declares the desired state. Then you have these kind of reconciliation loops. I'll get back to this in a bit. That actually makes it happen. Excuse me. And then you get a result. For example, you have three machines, and then you run Docker on all of these, and then it will distribute the containers accordingly. But it doesn't have to be Docker. Kubernetes can do many other things, many other container orchestrators as well, or container runtimes. And to demonstrate this, the what is more important than the how. If the request, if the desired state was just that there should be 100 web servers, then if there's nothing more declared than that, then any web server implementation will do. You can run some web service on your Raspberry Pis, some web service on your in your own data center, some web service on Google Cloud, some web service as kind of some function as a service in Azure. And that's still fulfilling the claim. If you want to be more granular than that and say everything should be running in Docker on my own data center, you can do that. But still, it's just a matter of how much you specify. What are the constraints? So the how is kind of dynamic in that sense. So that means that these interfaces or application programming interfaces, APIs, are key to defining a larger systems. And just as some of you maybe have used that, I have for sure used this kind of toy when I was little. You might as well. You learn how to make interfaces and how to fit things into interfaces. And then that's exactly how you build these kind of larger systems in real life, that you need to find some kind of representation for what you're internally modeling. Is it a circle? Is it a rectangle? Is it whatever? And then once you have that interface, you will also need to find some implementation of the interface that satisfies the contract. Let's see if there's questions at this point. Okay. So to take this as an example, these is it nine different Cncf projects. There's more, but projects that I just listed here have only a specification, only this kind of interface description, no implementation whatsoever. So they leave it up to everybody else to actually implement the thing themselves. And then there can be multiple different implementations. So for example, container networking is defined in Kubernetes using CNI interface. And then there's tens, like, I don't know, probably between 10 and 30 different network interface implementations. So with Kubernetes, you can use any of them. You don't need to, Kubernetes doesn't ship with one specific networking solution. You can use any one that implements CNI. Same thing for container distribution that is using the update framework. If you want to have storage in Kubernetes, and use CSI. If you want to instrument your applications, you use OpenTelemetry and OpenMetrics. If you want to isolate your applications, then you use Open Container Initiative, regardless of if it's a VM or container, and so on and so forth. So this is all what Cloud Native is built around, these specifications, and then implementations to those specifications. And that leads to quite a lot of good benefits for the ecosystem. So compared to before, where it was like this platform C and D, we now have a solid baseline for everybody to build their platforms on top of. So users, at the end of the day, want something. Generally, this is, well, a bit of a generalization, but still, users want some kind of solutions that fit their business needs. So they want to have the Heroku style that I was talking about. Like, I just want to do git push with my application, and then it should be up and running on the internet. That's what I care about. Or I want to have this user interface, so I see how all of the servers are doing. I want to be able to click there and there, and at that point, get me the right things happening. I don't want to go into shell scripts and all of that kind of stuff. So that's a platform that the user would be interacting with. And previously, the platforms have been really, really, like, all the way from the bottom to the top. They have been integrating all of these things. That's a lot of code. That's a lot of work for the one that is building the platform. And what do you do then to kind of minimize the amount of your work? Well, you only offer a certain smaller set of functionality. So say that someone is building a platform C, and then they only have capacity internally to provide for own data centers, Amazon Web Services, and OpenStack. That are the only kind of solutions that it can integrate with, because they are resource constrained on platform C. But similarly is platform D resource constrained, but they choose another way of working, and they do everything again from top to bottom, not sharing. And now you see that, or now you realize that the engineering work for platform C and D is actually duplicated in some sense. Engineers have worked on the same problems in platform C as they have in platform D. But they might not be overlapping. They might not have come to the same conclusions. They might not do it in the same way. There's no consistency. And they, on top of that, support different kind of platforms. Both support OpenStack, but then it's otherwise different. So if a user wants to change from platform C to D, they might not be able to, because platform D, for example, doesn't support running on their own servers. So this has been quite, and then it's also more costly. If the platform C has needed to put 3 person years, or more realistically 300 person years into building platform C, then they need to make still a profit. They need to, the solution need to be more expensive than platform B, which maybe could manage to only get to some kind of good state with only 100 person years. because they were reusing everything in Kubernetes or that already existed. So this is my what I want more industries to also realize, that by working together, every company is contributing to Kubernetes, to the shared foundation together, then everybody actually wins. You don't need to do as much work yourself if you have the capacity of every other company, some capacity of every other company as well. So that has worked out really well in Kubernetes and saved, well, I dare to say millions of dollars, if not even billions, in value. So that, and then on top of that, Platform B and Platform A all get the same benefits of all the features that Kubernetes has, and all of the platforms Kubernetes can interact with, they can interact with by default. They don't need to do much extra work for that. They need to integrate, of course, you always need to do that, but still, you have, it's a whole other story in terms of compatibility. So it's a separation of responsibilities. You figure out where is the platform should figure out where is your kind of segment that you want to target, then you build that, and then you reuse the rest. That is the promise of open source. Of course, it also means that you need to give back to the community. If you're doing something, if you're improving Kubernetes, if you're doing something good, if you're doing something that extends Kubernetes, you probably want to share that with others as well, both to get contributions from others, but also to give back value that you also have received from the community. So it's a platform for building platforms. So that's what we call a platform. So Kubernetes is a platform for building platforms like A and B and C and D if they would use it. So it's a better place to start. It's not the end. Kubernetes, you might not want to, as a user here in Ostrobothnia, for example, you might not want to use Kubernetes directly without something else, without some platform A, B, C, D on top. You might want to use some platform on top, but it just makes sense both for your bottom line and for your solution provider building the platform to use Kubernetes, because then you can move from different data centers and solution providers and all of that, still being interoperable with your earlier place. So it's a better place to start. It's not the end. And that can be visualized in this way as well. You can call it like Linux, but just for distributed systems. So instead of making kind of syscalls direct, like instead of programming your CPU directly and programming your RAM and GPU and SSD, you probably want to use some operating systems these days. And you talk to the operating systems using system calls or syscalls. Same way, instead of talking to every single machine individually, if you have 10,000 of it, 10,000 of them, it gets kind of boring. And yeah, that's why you use Kubernetes, which takes care of that for you. And it's all driven in this kind of API-driven way. So to keep the entropy and randomness and all of these things that we discussed that are inevitable under control, we figured out that we need to declare some desired state. And but that's not quite enough. We also need to observe where are we. We need to observe the actual state so we can compute some action plan to go from the actual state to the desired state. And this maybe sounds abstract, but if you think about a taxi, it's quite logical. When you call a taxi, you say, I am at this place at the moment, and I want to go to this other place. Can you pick me up and drive me there? So that's kind of, you do all of these things, all of these steps, but and then you can think of these as like coordinates. So like the actual state is one coordinate, and the desired state is one coordinate, and the action in between is like an arrow or something. But if you would just specify the arrow, if you would be saying something imperatively, then you would say in the sense of like, okay, hi, I'm Lucas. I want a taxi, and I want to go 50 kilometers southeast, but you can pick me up anywhere. Because it doesn't matter. It doesn't matter. I just want to go do the action. I don't have a starting place. I don't have an ending place. And that, of course, quite much, quite much less reliable if you actually have some state you want to end up at. So if we look at the example that we used earlier, there is this. Well, we ended up at this actual state. The blue distribution was where we ended up, but the green distribution is where we actually wanted to be. We wanted to actually upgrade one of the servers to v2 and not be running v1. We wanted to actually have all of the servers run configuration B because that was the better one, and they should be consistent. And we wanted to have 2 servers running because of the seasonal, not 3, but 2, because of the seasonal load. And we didn't want to have some server that was broken. So at least the first 3 of these actions we can fix in code, and we can fix them automatically even. The fourth one, the repairment of the server, might need human action, but that is the only one then. So if we kind of think about this as coordinates, then on one axis we can have how many servers are at operating system version 2, and on the x-axis we have how many servers are there at configuration B. And in the beginning we have 1 server at OS2 and 1 server at config B, and that's the actual state. But then we want to get to the desired state, and that's 3 servers at config B and 2 servers at version operating system 2. So then we do 2 actions, and by doing those 2 actions, we see that we got to the right place. But we might not be able to do it in kind of one jump. We might need to do it differently. But what is interesting about this example is that if these are actually independent actions from each other, now these might be dependent, but if these actions are independent, we can have multiple these kind of corrective actions that are executing at the same time, and not kind of doing it first this, then that, then that, then that, not in kind of this waterfall method. Instead, we can do it all in parallel, and that's what Kubernetes is doing. It's executing. Kubernetes contains 25, 30 or different these kind of loops, reconciliation loops that just check what is the actual state, what is the desired state, and try to fix them in parallel. So it looks like this. We have some desired state. We observe the target system. We observe those. We do a difference. When we take the difference, we figure out an action plan. And when we have figured out an action plan, the action plan might be 0. It might be nothing. If the desired state and actual state already equal, then nothing to do. We just loop. We just wait a couple of more minutes. But if there is an action, then we execute the action. We act. Then there will be some result of the action, and that we might report to other consumers. So like we want to send an email if the action failed, or we want to put it on some dashboard that this is not working, etc. And then after that, when we have done all of that, we just wait and then requeue. Then in 5 minutes, we maybe check again the same thing. So, well, I already put this example, but like if a person wants to go from Jakobstad to Nykarleby, then they tell their desired state, the actual state, then there's an action plan, some kind of route to take. There might be multiple action plans, and the route plan is not well defined. It just depends on the conditions that day. And then the action is executed. Then either the action was successful or it was unsuccessful. Maybe the taxi driver wanted to go to Nykarleby, but into the GPS, they put Karleby, and then they ended up in Kokkola. And that was not the desired result. But still, like, there will be some result. And then they will make some kind of report to someone else that, okay, now I have driven this person to Nykarleby, and that's kind of, well, maybe a social media update or something like that. And then they will find the next client, and then it goes on and on. So we kind of have a paradigm shift from that we are operating machines. We are operating the service directly ourselves, like we were doing before, to that we operate automated processes that operate the machines. So we're putting ourselves on the next layer, but that's nothing new actually, because say take the Industrial Revolution. First, we were actually weaving things, for example, textiles ourselves, but then we figured out that, or doing some other chemical process or similar, or biomedical, or you name it. But then we figured out we can automate that and have some automated process that does it for us, some robot, and then we will monitor the robot instead. So that's just the same thing here. In that sense, nothing new, but now we just have a means to do it. And let's take let's check how is the imperative flow and the declarative flow different. So if you have an imperative flow, then you will have a web UI, for example. The administrator clicks that, and then there will be some corrective action that the administrator clicked to the system that is being operated. So say that there's too few web servers available at the moment. The system is red. The administrator clicks and fixes the system, and now it's all good. It's in a correct state. Perfect. Then administrator goes home, goes to sleep, whatever. And while they are asleep or at home, the system gets some emergent change, state change, and now it's in a faulty condition again. So either nothing happens, or the administrator needs to wake up 2 a.m. at night, which is not so nice. So the declarative example of the same thing is that the administrator defines some desired state. It goes into some store, some kind of database or similar, which is Kubernetes in this case, or which could be Kubernetes. And not at the same time, but say a minute later or a couple of seconds later, the reconciler, this kind of checking every time, then it will get the desired state. It will figure out, okay, well, I am running 90 replicas, but the load is so high, I need 100. And then it will scale up by 10. And that's something you can kind of codify and then do just fine. Then administrator goes home, goes to sleep, and while they are at home at sleep, then 120 replicas will be needed. Same problem as earlier. Now the difference is that the reconciler can again check that, okay, we actually need more now, and we depending on these metrics and whatever, I will scale it up by 20. And now self-healing system is good again. No action needed from the administrator. So this is the kind of self-healing pattern, the higher development velocity, and all of these cloud native benefits that I was talking about in the beginning. So yeah, I think I have millions of slides from that I've made that I can do now or later, but I think this is quite a good place to stop.